Dear audience, I welcome you to my presentation here. My name is Marcel Joss and I'm a lecturer at the University of Applied Sciences in central Switzerland. Originally it was foreseen that Mr. Kaufmann would have the speech here, but he got his diploma in engineering, diploma in engineering this summer and has already left our school, so you have to leave it me now. I will talk about two different issues concerning our ground station. First will be enhancement of our antenna control system, and the second one I will talk about a little bit of the implemented protocol stack and the correcting scheme in our CubeSat project. We have seen a similar fact figure sheet already in the presentation before, so therefore I just mentioned 2 points related with the science of the payload. Actually, we have up to 10 GNSS receivers, which measures the raw data from the GNS networks, and we have to bring down the compressed data from those receivers down to Earth. For that, we have a communication link up there with a gross data rate of up to 9,600 bits per second. So even we compress the data on satellite level, it will be very difficult actually to bring those huge data down to Earth without too much errors. Let's have a short look on an ideal downlink budget. CubeSat will transmit again with plus 30 dBm, which conforms to 1 watt power. We will lose probably some power with the connected cable and impedance losses at the satellite. I included this with minus 2 dB, and we expect a certain antenna gain. We try to use a monopole antenna, and an ideal monopole antenna promises you 5 dB gain versus an isotropic radiator. The distance between the ground station and the satellite, if we take the foreseen orbit height with 550 kilometers and an elevation angle above 10 degrees above the horizon, we will have a distance of up to 1,815 kilometers. And if we calculate the free space loss, it contributes to minus 150 dB. According to the recommendation from IQ, the P618 for the frequency we use, there will not a lot of signal absorption through the atmospheric or the ionospheric layer. We will have a certain antenna gain at the ground station with 24 dB, and I also included some polarization losses and connected cable and impedance losses again at the ground station. So if you sum up all those contributions, we end up with power at the receiver with minus 101 dB. We are using a Kenwood transmitter or transceiver TS2000, and it shows a receiver sensitivity of minus 120 dB. So everything seems fine. We have a link margin with more than 18 dB. However, in that ideal link budget calculation, there are many things not included, and probably you see some aspects. Let me start this small video. Whether it works. No, unfortunately not. Missing things are the ideal UHF monopole antenna will never give you this 5 dB gain, because this antenna will never have an infinite ground plane on a 1-unit CubeSat, and we will also have some mutual coupling between the other antennas, with the VHF antenna, which is used for the uplink, and another UHF antenna, which is used for the beacon signal. We will have some dynamic and static antenna pointing errors, and those can produce serious problems especially when we use high-gain ground station antennas. And a third aspect, our signal on the UHF frequency will face quite strong signal fading phenomena in the ionosphere due to the scintillation effect, especially for low elevation angles. So those pointing errors, they could have different sources actually. There might be an offset between the mechanical axis, the antenna electrical axis, or there might be some thermal deformance, line forces, who will produce some lag or error in the pointing. And to handle with those things, we use actually our 4 receiving antenna together with the feeder network to produce correction signals. This feeder network consists of 3 4-port hybrids and 1 3-port combiner, and then we are able to produce a sum signal as well as a different signal for azimuth and elevation. And if you make a phase discrimination between the sum signal and one of those different signals, you get a signal which corresponds to the off-axis error. Why do we need channel coding? The thing is that we have a wireless link between the satellite and the ground station has just a moderate quality, and we will have a certain packet error rate. On the contrary, we have a science load which produces quite a lot of compressed data, and just a few bit errors can make them very quickly useless. So therefore, a downlink connection with high reliability and a low packet error rate is significant for the success of the mission. That was the reason that we have implemented actually a protocol stack which corresponds to the CCSDS recommendation for the space link. However, we have simplified it. We have not implemented the transport layer and not the network layer. The error situation we handle twofold. On the data link level, we have a forward error correction concept, and if undetected error packets will up at the application level, we try to detect them with the frequency checksum. Faulty packets will then just drop, and this will lead to a timeout on the transmitter side, and the packet will retransmit it again. For the coding itself, actually, we followed also the CCSDS recommendations. For the uplink, we are using the BCH code, which has a capability of correcting 1-bit errors. On the downlink side, we are using a concatenated coding concept, which consists of a Reed-Solomon code as an outer codec and a convolutional code as an inner codec. So let's wrap me up this presentation. CubeETH is a 1-unit CubeSat, and its main mission is to measure quantity to high accuracy using up to 10 GNSS receivers. They produce a large compressed data. We have to bring them down to Earth without errors actually for post-processing reasons. Our ground station uses a high-gain antenna with 4 UHF antenna. Together with the feeder network, we produce some correcting signals that we can reduce the pointing errors. And to get a high communication link in the downlink area with a low packet error rate, we use powerful downlink channel coding concept with a concatenated code of the Reed-Solomon and the convolutional code. Thank you very much for your attention.
We have time for a few questions, if any.
I have one. Do you plan to estimate also the position of the satellite with your calculated error of your pointing on ground? Like you want to triangulate the satellite with the ground station?
No, actually, the only what we have to bring down is just the raw data from the GNS as receives possibly without any errors. Post-processing will be done by the ETH in Zurich, and not, so far as I know, they will not include some quantum errors coming from the ground station.
Okay, thank you.
Any other question?
Would you consider the 3 dB advantage of the polarization error we had on transparencies, adding additional antennas you can correct on that?
Sorry, I didn't.
The question is, what would you consider to improve on the 3 dB disadvantage that you have on your lead budget because of polarization error?
Not really, no. We try to leave it. Actually, on the ground station side, we have cross-dipole antennas, so probably we can have a benefit from that.
Any other question? Okay, so thank you very much, Mr. Chess.